today we're going to talk about titration. Titration is just a process by which we help understand the neutralization reaction. It's a technique to neutralize an acid with a base or base with an acid to find something unknown. So here's really what we're working with in terms of a problem. We have hydrochloric acid and sodium hydroxide, and they're going to react together to produce water and a salt. This salt this time really is NaCl. And here's the deal. We don't know the molarity of the acid. This is our unknown in this problem today. So we don't know the molarity, but here's what we do know. We do know that I have 0.500 molar sodium hydroxide. How did I make that up? Well, just a review. This is 0.5 moles per liter. So what I did is I looked up the molar mass of sodium hydroxide. That was 40 grams. And I took half that amount, so 20 grams. I dissolved that into a liter of solution. So that's how we got our 0.500 molar sodium hydroxide. What did I do with it? I poured it into my burette. So here's what we're going to do is I'm going to take some of my unknown acid and I'm going to use just a beaker. Sometimes we'll use a flask when we do titrations. We're just going to use a beaker. A lot of times that's just a little bit easier to navigate. We're going to use a pipette to measure out exactly 10 milliliters, or as close as we can to 10 milliliters. This is much more accurate than using a graduated cylinder. So we're going to put this little hand pump on the end, and what I'm going to do is put it down in my hydrochloric acid. There's a little roller wheel here, and as I roll that up, what that's going to do is that's going to bring my hydrochloric acid up into my pipette, and I have pretty good control over it. I take this out, go to my beaker, and I can either hit the button to release or I can actually roll it back down. So I've just added 10 milliliters of this unknown hydrochloric acid to my beaker. Okay? Now, most of the time when we do titrations, that's not a lot of volume. And so we will typically add some distilled water to it. What does that do? Well, does that add any H pluses? Does that add any OH minuses? None at all. Water is neutral. So if we add water to our beaker, all this does is kind of water and dilute our acid, but it actually still keeps the same amount of moles of acid or base in our beaker. The other thing we're going to do is we're going to add a stir bar so that I don't have to keep swirling. We're going to add a stir bar and we're going to put it directly on a stir plate. And what that does is that will continuously stir for us. Now, how are we going to know when we neutralize the acid and the base? Well, that's where we use an indicator, phenolphthalein. Phenolphthalein will be colorless in an acid solution, acidic solution. If it's in a basic solution, it'll actually turn kind of a magenta pink color. So I'm going to put a couple drops of my phenolphthalein in there, and notice it doesn't really turn it pink or anything, it's just a clear color. Why? Because all I have in the beaker right now is acid and water. It's kind of hard to see on my stir plate here, so I'm going to put a little piece of paper behind it that will give you kind of a white background so you can better see what's going on. Now, the goal of this is to put enough base, sodium hydroxide, in the beaker to neutralize the acid. We're going to have to put just slightly more than the exact amount. We get to what we call the endpoint. It's a color change. So we're looking for our indicator to tell us that we went just past neutralization and turned it a little bit more base or basic, and that will actually turn the phenolphthalein a pink color. So before we start, we have to take a good reading on the burette. On the burette, you got to read the bottom of the meniscus. So if I look closely here, I feel like I'm about 22.1 milliliters. So I'm going to write that down. I'm starting at 22.1 milliliters. And then what I'm going to do is slowly but surely, I'm going to open the valve and I'm going to add my base. Now I've done this, so I kind of know how much we're going to add. So I'm probably going a little faster than I would recommend for you. And I don't want this to take 10 minutes on a video. So I'm going to add about 10 milliliters before we really slow it down. So I'm now at about 30 milliliters. I'm at about 31. And what you're going to notice as I continue to add is if you look kind of right in the middle of the beaker, you might be able to see that there's a little bit of pink showing up. Now, as soon as the base hits the beaker, there's some phenolphthalein in there that will react with the sodium hydroxide and it'll turn it pink. But as you continue to mix, that sodium hydroxide actually helps neutralize the acid. So the acid and the base react. Since water is neutral and we also have this salt in here, that pink color actually goes away. So we're going to keep doing this until the pink stays. That's our goal. Our goal is to one drop change the color from clear to a light pink color. So I'm going to keep going and put some in here. As it gets closer, I'll kind of slow it down. So you notice this pink color, it's staying a little bit longer. And if you kind of look, it just hovers in the middle of the beaker, which is kind of cool. So we're going to keep adding a little base. And I'm getting down to where I'm going to look a little closer and kind of watch my numbers here. Just add a couple drops at a time. Notice that pink is staying a little longer. Staying a little longer. And we're just going to start doing just a little bit at a time. Double check that our pink goes away. Notice that pink is staying. It takes a little bit. Once it mixes, it does neutralize the acid, but there's still more acid or H+ ions in the beaker, and because of that, the phenolphthalein is still this colorless or clear color. Add a little bit more. That pink is still hovering. We got to make sure that it goes away. Once we know it's gone, then we can add a little bit more. Add a little bit more. And we're going to kind of start going slow here, like one drop at a time, and make sure that it goes away. Well, that pink is staying. Again, let it stay. Once it goes away, then we add another drop. Our goal is just a hint of that pink color that will stay for at least 15 seconds. And we have to be patient and carefully add just one drop at a time. Pink is there, goes away, add another drop or two. That pink is still sticking around as it continues to spin. Again, the acid and the base, they react together. We still have a little bit more acid than base in our beaker, and that's why it's colorless. We're getting super close here. The pink is staying. Let's see, maybe one more drop will do it. Let pink, come on, go away or stay. Do something, right? One more drop. You can tell it's starting to kind of shift back and forth a little bit. It's right on the line. It seems to stay pink and then go clear and then stay pink, go clear. It's going back to clear, so let's try one more drop. There you go. We have all pink. We'll let it sit for a few seconds and we'll just double check that it stays. It looks like at this point, I would say it stays long enough. So we go back to our burette and we read, and it looks like to me about 43.3 milliliters. So we take 43.3 milliliters. That's our end amount. What we do is we subtract and we find the difference, and we find that we used 21.2 milliliters when we did our titration. So it took 21.2 milliliters to neutralize our acid. And that is where we pick up with the calculations. All right, College Chem, welcome back. Today we're going to talk about titration problems. And really all titration is Titration is a process we use to actually determine the unknown concentration or unknown about one of our solutions. And we're kind of tapping into the idea that an acid and a base, when you mix them together, they react to produce water and a salt. So they neutralize each other. And so titration is the process of using a known concentration, whatever we know, either the base or the acid, that concentration. We use that by putting it in the burette. You see here the burette on the picture here. Water level, we start out at the top, whatever's in the burette, and you actually open the valve and the liquid lowers down. We can actually use that to figure out how much base or how much acid it took to neutralize the other substance. And from that, we do calculations. That's really what titration is. In the scenario that I showed with you a few minutes ago in the actual titration problem, and you actually saw me add sodium hydroxide to the acid, that's basically what's going on. Is we put the known concentration, the sodium hydroxide, in the burette. We put a certain amount of acid in the beaker or flask below. And then as we start this process, what do we do next? Well, we drop the base into the flask. And as we add the base into the flask, we're neutralizing the acid. What's really going on at the particle level is the H+ ions and the OH- ions meet each other and they create water. And then there's leftover ions that we consider to be an aqueous salt in solution. Usually when we're doing a titration, we add a indicator. Indicators will change colors and show us the point which we should stop and do our calculation. So when we did the example, we put some phenolphthalein in the flask or in the beaker. It starts out clear because phenolphthalein is a natural indicator and it's clear in an acidic solution. And as we continue to add the base to that, the base mixes and reacts with the acid. Then in that process, we start to see a little bit of that pink magenta color show up. And we keep doing that until we get just barely enough, one more drop of the sodium hydroxide to turn the phenolphthalein a pinkish color. When that happens, that's our end point. We stop and we record the volume. And then we do a calculation from that to figure out how much base it took to neutralize our acid, right? So start a titration, excess acid. In the middle of it, we start to see that color change. If we continue going over, we get that excess of base, and that's what that pink is. Our goal is to have one drop change at that color. All right, so here's the problem I'm going to work out with you, and this goes back to the lab data that I collected. You perform an acid-base titration to standardize an HCl solution. In other words, we're going to find the concentration of the HCl solution. We put 10 milliliters of our unknown concentration of HCl in a flask with a few drops of indicator solution. Our indicator was phenolphthalein. Then we used the 0.500 molar sodium hydroxide in the burette. We took the initial reading. My burette was reading 22.1 milliliters when I started. We continued, we did the titration, and we stopped when we got to 43.3 milliliters because we saw the color change. So the next thing that we did is we actually calculated what volume of sodium hydroxide we needed. We took our 43.3 milliliters and we subtracted 22.1 milliliters. And that told us that it took 21.2 milliliters. So I'm going to write that down over here, 21.2 milliliters. We know the concentration of sodium hydroxide is 0.500 molarity. Here's what we know about the acid. We used 10 milliliters, but what we don't know is the concentration of the acid. So we go back to our concept we talked about before. When we know molarity, molarity is moles over liters. And one of the most helpful uses of that equation is if we cross multiply, we get, and we're going to do this for sodium hydroxide, we get molarity times liters equals moles. And if we do that, we take our 0.500 molar sodium hydroxide, and then instead of using milliliters for sodium hydroxide, we really need to convert that to liters. So we take our 21.2 milliliters divided by 1,000, and that gives us 0.0212 liters. We multiply those two together, and what that tells us is that we have 0.0106 moles of sodium hydroxide. Okay. Now, since we have 0.0106 moles of sodium hydroxide, and we look back at our balanced equation, we see that this is a 1:1:1:1 ratio. So what we can do when we start thinking about the acid is we can say, well, if I know that I have 0.0106 moles of sodium hydroxide, my ratio is for every 1 mole of sodium hydroxide, I have 1 mole of HCl that's needed. So because this is a 1:1 ratio, we actually know that in our flask or beaker, we must have had 0.0106 moles of HCl. Okay, and you can probably see where we're going from this. So now if I wanted to calculate my molarity, since molarity is just moles over liters, I can take my 0.0106 moles of HCl and divide it by the volume. My volume is 10 milliliters. So I take 10 divided by 1,000. We got to put it in liters. That's 0.0100 liters. And when I punch this into a calculator, 0.0106 divided by 0.0100, I get 1.06 molarity HCl. So my molarity of my hydrochloric acid must have been 1.06 molar. Okay. Now, we're going to move on. We're going to do a second problem on the next slide. So let me clear this. We're going to do one more. Here is our next titration problem. It says, what volume of 0.250 molar barium hydroxide would neutralize 25 milliliters of HCl solution in the problem above? Well, the problem above we just did, and we found that our molarity is 1.06 molar hydrochloric acid. We know that the molarity of barium hydroxide is 0.250 molar. What else do we know in the problem? It says that it would take 25 milliliters of the acid. So we know that we used 25 milliliters of my acid to neutralize the base. What I'm trying to find, what volume, either in milliliters or liters. Since the problem gives milliliters for my acid, I think I'll end up answering in milliliters. So how do we do this problem? Well, it's the same process as before. Go with what we know the most about. Hey, that's our HCl. And we take our molarity times liters equals moles. And if I calculate this, I take 1.06 times 0.02500. Remember, we have to divide the 25 by 1,000. That gives us 0.025. Keep our sig figs 00 times the molarity 1.06. That tells me that I have 0.0265 moles of HCl. Okay. Now, think about the balanced equation. If I want to figure out how many moles of base that is, I go back and I look at my balanced equation. This is a 1:2 ratio. So what I'm going to do when I want to start thinking about barium hydroxide, I have to use that ratio. So I take my 0.0265 moles of acid and I get rid of moles of acid, 2 moles of HCl per 1 mole of barium hydroxide. Because of that, I really cut the number of moles in half. So I divide by 2 and I get 0.013, whoops, 0.0132, boy, I can't write today. That's a 3. 0.013, and then I see a 25. I'm going to round this up to 3.0133 moles of barium hydroxide. Okay. Now, what do I need to find? Where am I going with this? Remember, I'm trying to find volume. So this might take you back a little bit here, but in order to find volume, again, remember our molarity equation is moles over liters. If we cross multiply, we get molarity times liters equals moles. Well, if we wanted to get the volume by itself, liters, we would end up dividing both sides by molarity. And that would give us liters is moles over molarity. So when I want to do my calculation here, I'm going to take 0.0133 moles divided by my volume, divided by my molarity, which is 0.250 molar. So I take that number that's in my calculator divided by 0.25, and I get 0.0530 liters, or if I multiply by 1,000, I'm going to get 50, is that right? I think I multiplied by the wrong thing. 0.0530 times 1,000, you get 53.0 milliliters. That's how many milliliters I'm going to need to neutralize that acid. There you go.